Okay. Good afternoon, everyone. On behalf of ETA Florence Renewable Energies, technical organizers of today's event, I welcome you to IEA Bioenergy webinar series. Today's event is titled Sustainable Aviation Fuel, Biojet Technologies, Commercialization Status, Opportunities, and Challenges. The event presenters of today will be Jack Sadler from the University of British Columbia in Canada, Susan Van Dyke, also from University of British Columbia, Vancouver, Canada, Geoffrey Touvette, Vice President of Operations and Sustainability of FSM Group, Canada. The event will be moderated by Jim McMillan from the National Renewable Energy Laboratory from the US. I will give you a couple of instructions on how to interact with the speakers. You can submit the questions via the Q&A tab at the bottom of the Zoom window. Questions will be replied either via the chat by the panelists or live. Again, so please use the Q&A tab for questions, not the chat. The webinar will be recorded, so you will be able to find the recording of the webinar and the presentations tomorrow on IEA Bioenergy's website. This is all from my side, so I wish you all a pleasant webinar, and I yield the floor to our moderator, Jim McMillan.
Well, good day, everyone. Welcome to the webinar. We're glad to have you. I just wanted to make a couple remarks before we start, and I'll come in at the back end and do the moderating. But the outlook for biofuels over the past decade has shifted dramatically towards from sort of providing biofuels to all sectors to really focusing biofuels to the hard to electrify sectors. And most hard to electrify of all is aviation. So it's a very key area for biofuels development now and getting a lot of attention. And so thus this webinar. So my colleague leading IEA Bioenergy Task 39 is Jack Sadler, and he's going to make some brief introductory comments about Task 39 and the report, and then he will introduce Susan to give the main presentation, and she will introduce Thomas. So Jack, I yield the floor to you in the interest of time. Thank you.
Thanks a lot, Jim. Lupo, I wonder if you could go back one slide to the introductory slide, please. Perfect. So Jim, thanks a lot, and I look forward to you moderating the discussion at the end. And thank you to everybody at the different time zones for joining us early in the morning here in Vancouver. So Susan, my colleague Susan Van Dyke is going to be presenting the main body of the report. We're lucky enough to have Jeff. I'll mention Jeff later on, and then we will hopefully have an interesting moderated discussion at the end of the presentation. Next slide, please, Lupo. So IEA Task 39, we benefit from these 16 different countries and these different champions who are all presenting who all represent the different countries. Next slide, please, Lupo. And Task 39, I think Susan's going to be focusing today primarily on some of the technology, but as she'll also be covering is the policy. We need the policies to drive some of the sustainability initiatives. How do we move off of fossil fuels onto more sustainable feedstocks? And if you've got time, we've got the website there, Task 39. I encourage you to go into the Task 39 website. And as you'll see, next slide, please, Lupo. You'll be able to see really what the work that we've been doing. Today is specifically about biojet fuel or sustainable aviation fuel. And as Susan will cover, it needs both technology push and market pull. And we have various reports on the website that you can use. Next slide, please, Lupo. And these are examples of some of the reports that are posted and publicly available, all the way from drop-in biofuels right through to the Biojet report. So the Biojet report, the SAF report is actually online if you want to reference it. Next slide, please. So specifically, we have our colleague Mahmoud Abadian has been coordinating what we call the Implementation Agenda report. This is really a comparison of the different policies that are used in the different countries. And I draw your attention to policies such as the low carbon fuel standard. So rather than a volumetric target of so much ethanol, we're really looking at the carbon intensity of the fuel. So this leads into some of the work on different models, such as the Greek model or the GH Genius model, Next slide, please, Lupo. Other topics that hopefully will be covered in this series later in the year is on biomarine fuel. This is led by our Danish colleagues. One of the ways, the modus operandi in our task is to leverage, is to take a champion. And as many of you know, Denmark, with companies such as Maersk, is very much a leading country in terms of looking at biofuels for marine applications. Next slide, please, Lupo. In the same way, our colleagues in Brazil have been at the forefront of biofuels, particularly with ethanol production. And another report that's actually posted on the Task 39 website is a comparison of the different LCA models. So again, I encourage you to go on the website, look at these reports. And again, the tasks make use of all these leverage from the expertise in the different countries. Next slide, please, Lupo. And one area mentioned in Canada is the work that we've been doing on co-processing. The big benefit with co-processing is we're able to engage the oil sector, because the oil sector, I think, recognizes it's got to decarbonize as well. So if you go online and look at the co-processing report, you'll find that that's one way of making use of the current infrastructure, and it's one way for the oil sector to try and decarbonize. Next slide, please, Lupo. What we're going to try and cover today, this is another report that's posted on the website. We were fortunate to get funding from Boeing. The other benefit of Task 39 is very good industry involvement. So we've had companies such as Boeing or Sky Energy. And one of our speakers today, Jeff the Vet, worked for an airline. And so we're lucky to have industrial representation on the presentation today. Next slide, please, Lupo. Because Jeff was involved in this ATM report, which is posted again on the website, which really looked at different biocrudes that were produced at different parts of the world. You can see we got biocrudes from VTG in the Netherlands, VTT, Aarhus. And again, I encourage you to look at this report, which looks at the opportunity to co-process biocrudes. Next slide, please, Lupo. But really, this is my last slide. And I think the focus today is really on sustainable aviation fuel, biojet fuel. And I'm very fortunate to work with my colleague, Susan Van Dyke. And Susan's really going to present the report, and hopefully you'll find it interesting. And if you need more details, please ask us questions. But again, this report is posted on the website. So Susan, over to you.
Thanks, Jack. Okay, next. Yeah, so today I will be presenting basically on the report that we have just published on Biojet Sustainable Aviation Fuel Commercialization. And although the focus is mainly on the technology potential and challenges, I'm going to cover a couple of other topics as well. Next. So I think if you've been reading the news, you must have seen that SAF developments have seen a significant acceleration with daily announcements in the media. And even for a person in the area, it's almost impossible to keep up with all the announcements, the reports, the webinars coming out. So I think there's a lot of excitement around SAF. Next. So although, I'm going to start off with some of the take-home messages from this presentation, just so to give you an overview. And firstly, I think what we conclude in this report is that there is no silver bullet technology and that all SAF technologies should be commercialized. Secondly, I think the large price gap with conventional jet fuel is the biggest challenge for expansion. It's not so much a technology issue. Then it's really the right combination of policies that will be the most important driver of expansion. And I will briefly discuss some of the policy issues. And HEFA production for SAF is currently the only commercial technology out there and will continue to be the biggest supplier in terms of volume of SAF up to 2030 and perhaps even beyond that. So currently, what I will look at from a technology perspective is that 15% of all current renewable diesel production facilities can immediately be diverted to SAF with low investment, which just on a theoretical basis will be 1 billion liters. Obviously, with announcements from Neste and so on, the actual numbers will be significantly more. And as we have seen also in the news, the first fully commercial facilities for other technologies such as gasification and Fischer-Tropsch and alcohol to jet will be coming online in the next few years. And this will likely lead to a rapid expansion of more facilities. Now, power to liquids have gained a lot of attention, and this will play an important role for SAF production, but will likely only be significant after 2030. Pyrolysis and HTL technology pathways have great potential, but will only become significant likely after 2030, partly because it's still at a lower technology readiness level, and there is no current ASTM certification for this technology. Next. So as I said, I'm going to cover a number of topics such as SAF availability, scale up and commercialization, biggest challenges, drivers, feedstocks, sustainability, and then I will spend quite a bit of time on the technologies. So I'm not going to start off by presenting the whole rationale for why we need SAF. I'm assuming that that is old news, and so I'd rather spend the time covering some topics. Next. So if you go on the ICAO website, you will see these green, looks like water droplets, but basically saying that over 315,000 flights have flown with SAF, 8 conversion technologies have been certified, and 13 airports regularly are distributing blended SAF. Of course, this is a continuously increasing number. So current production in 2013 to 2015, we only had about 0.29 million liters per year. And in 2016 to 2018, this went up to 6.45. But in 2019, this suddenly increased, and Neste alone produced 125 million liters, apart from the contribution from world energy. And this is going to dramatically increase, with Neste announcing SAF capacity by 2023 of 2 billion liters per year. And on the others, on the right-hand side, you will see the from the ICAO stock taking seminar in 2019, the projections towards 2032, showing capacity of up to 8 billion liters. But as I will show, this is not necessarily all SAF, and there's decision-making from the producer how much of this will actually go into SAF. So if we look at how much SAF we are going to need, this is quite a tricky question. Current jet fuel demand is about 360 billion liters per year, and the volumes required by 2050, if 100% replacement, obviously this is going to be a significant challenge, but there are some studies by ICAO that has looked at the impact of electrification, increased efficiency, etc., etc. So that is probably a good place to look at more detail on this. But to put it in perspective, also currently ethanol and biodiesel only produce about 150 billion liters per year. So that it is a significant challenge. Next. So when we look at the potential technology commercialization and future SAF supply, as I said, we don't believe there's any silver bullet technology. All technologies should be commercialized to contribute to the volumes, because each technology can make use of niche feedstocks and different regional contributions. So the way we see increased volumes of technologies is really HEFA will continue to be a significant portion, but gradually in the next 5 years, we'll see gasification, Fischer-Tropsch, alcohol to jet, catalytic hydrothermolysis starting to contribute to the volumes. And gradually, I think over the next few years, we'll also see co-processing coming in, although there was an announcement today about co-processing SAF being sold by Air BP. And then after 2030, there will be an increase in all these technologies and potentially also co-processing of biocrudes, pyrolysis, HTL, and PTL, power to liquids, will become more significant then. And I think after 2050, PTL will definitely take on a much, much bigger role in terms of SAF volumes. Next. So the price of SAF is really a huge challenge. And if we look at the current price and prospects for price parity, so HEFA-SAF, we don't have any information about actual contracts with airlines, but information published by Argus Media and Green Air show about 3 to 4 times the price of conventional jet, between roughly $2,000 per ton and $2,300 per ton US. Compared to conventional jet fuel posted on 23 June was about $615 US dollars. So there's a significant price gap, and this will remain a huge issue, which I'll discuss under the drivers. But when we look at the other technologies, they are not commercial, and only techno-economic analyses are available, which generally give an idea of the minimum fuel cell link price based on a net present value of 0. And there's a very, very big range. Some technologies give an MFSP of $1,000, $1,500, while others go up to $7,000. So it's, but it's quite hard because many of the papers have different numbers for the same type of technologies, and different assumptions are being used. So I don't think that is very reliable necessarily. Also, I think the price that we see is based on volume, because the value of carbon intensity is not taken into account. And I think this is an important issue that will be addressed by some policies, that very low carbon intensity SAF should have a greater value than a high carbon intensity SAF. And price is definitely considered one of the biggest obstacles to airlines. And if we look at the price parity, it is possible that we will always see SAF being more expensive than conventional jet fuel, even though there will be significant cost reductions that will take place. But there will be many factors such as carbon pricing and so on that will impact this price parity. Next. So SAF-specific policies will have the greatest impact on SAF expansion. And the first 3 bullets there show some of the policies that have already been implemented. In California's low carbon fuel standard, aviation is included. The US Renewable fuel standard also includes SAF, and there have been several mandates and proposed mandates, for example, Norway, Sweden, Finland. And but I think what is important with that I want to point out with the California low carbon fuel standard is that shall we say, the incentive, the policy is linked to the carbon intensity reduction that can be offered by the SAF. But I think, you know, we've been talking about policy for many, many years. And for the first time, there are 2 significant policies on the horizon that is going to have a very, very big impact on SAF. The first one is in the EU, the Refuel EU proposed mandate, which the details will be announced tomorrow of this proposal, and potentially a 2% increase or mandate in 2025, moving up to 63% in 2050. But I think what I want to point out is that this mandate is based on volume. So it's a volumetric mandate, and therefore will create a significant demand for SAF. But on the other side, we have the proposed Sustainable Skies Act that has been announced in the US. And this has been a proposal for a blender's tax credit, also linked to carbon intensity reduction. So producers or suppliers can earn $1.50 per gallon and then increase up to $2 per gallon for 100% emission reduction fuel. And this is obviously from the supply side. So both are are equally important. But I think the importance of a link of the policy to carbon intensity reduction is really important, and I will point to some of these reasons in another slide. And I think something significant that has been happening is, although we've seen some voluntary corporate actions over the years where consumers of airlines can buy offsets and so on for their contribution to, for emissions. What we are seeing now is the development of buyers alliances, such as the Sustainable Aviation Buyers Alliance, and this could potentially create a very strong demand signal. And what is important is this is going to be irrespective of national policies. And the Sustainable Aviation Buyers Alliance, for example, they are projecting potentially a demand for over 2 billion liters of SAF by 2025, which is going to have a similar impact to, say, the mandates, but this is not going to be linked to national policy. And then also what I'm going to talk about briefly is the whole issue of SAF certificates, the ability of corporates to purchase the sustainability attributes of SAF without actually being buyers of fuel. Next slide. So from a technical perspective, I just want to discuss an issue which can be strongly impacted by policy. So currently we have a significant volume of renewable diesel or HVO produced, but so far only World Energy has regularly produced SAF, and Neste is going to, or has been and is going to significantly increase their SAF production. But basically, from a technical perspective, HVO producers don't have to produce a SAF fraction, because making SAF is more expensive than the renewable diesel only. And what I would like to show with the diagrams here is that you don't have to make SAF. So the first graph on the bottom left shows a gasoline, jet, and diesel based on boiling point and carbon number. And what you will see is essentially that the jet fraction and the diesel fraction overlap. And even if you want to do a gasoline or naphtha fraction, that can also overlap with the jet fraction. But as the figure on the right shows, that each refinery decides on certain distillation cut points in order to produce the products that they want to sell or that they see as valuable. So unless the jet fraction has significant value, a producer can decide to not produce any jet. And that's what's been happening with renewable diesel producers. There is a portion of jet, 15% at least, but there has been no value for the producer to actually produce that jet fraction unless there's some kind of a policy. So what we have seen is a policy called the fuel multiplier, where the SAF can earn more credits than the renewable diesel, which makes the SAF more competitive and therefore encourages the renewable diesel producer to separate out the SAF. And this is, from a technical perspective, quite important. Next slide. So here I basically show this figure from ICCT that shows a couple of SAF technologies, and that all of them, apart from the farnesene production, produce multiple fuel products with different potential ratios of SAF. So the normal HEFA route produces mainly renewable diesel with a 15% fraction of SAF, but this can be potentially increased to 50%. And gasification is similar, alcohol to jet similar. So what I'd like to emphasize is that the capacity of a SAF facility is actually not all jet fuel. And So a SAF fraction can be separated through distillation from the remainder of the products, and that this fraction can actually be increased through hydrocracking and isomerization. But in the process, when you are maximizing the SAF fraction, this comes at a cost, because as you are breaking up the molecules, you are lowering the liquid fuel yields, and you are also increasing the hydrogen consumption. So there's an increase in cost. So policy is one of the important drivers for maximizing SAF production. Next slide. So just to switch to SAF sustainability and potential emission reductions. So CORSIA has established minimum sustainability criteria, and RSB and ISCC have been certified sustainability certification bodies under CORSIA. So, and what I want to emphasize, although I'm going to talk about potential emission reductions, this is only one part of sustainability. So the table on the right really shows the default life cycle emission values that CORSIA has established for eligible fuels. But what is important is that SAF producers can demonstrate actual values that are better than these. So I think the impression that is being created is that some pathways seem inherently better than others from a carbon intensity point of view, but this is not actually a static metric. Recently, many SAF producers in the US, particularly from recent webinars that I've watched, are actually moving to net zero fuels based on adding renewable energy, for example, solar panels or wind energy as part of their SAF production facility, and even carbon capture and storage. And what this means is that they can achieve a net zero fuel regardless of the technology. And I think what is also significant is that a SAF production facility can be built from the start to take this into account. But this will only really happen if there's sufficient value placed on the carbon intensity, because obviously this will cost more, and that is really the importance of the carbon intensity. Next. So just to switch to feedstocks, because this is a question that everybody wants to know. Do we have enough feedstocks? So there are so many reports coming out all the time, and many of them say feedstocks are not considered limiting for SAF expansion. But I believe that this is probably overly optimistic because firstly, the cost of feedstocks are ignored. So in HEFA and some of the other technologies, feedstock cost is the most significant contribution to the cost of the fuel, and ignoring the cost really doesn't make sense, because practically then it's not really available. Then there's obviously competition for feedstock with other applications, for example, biodiesel. And then there's a difference between theoretical and actual availability. So some of the feedstock availability for, say, lipids for renewable diesel or HEFA-SAF is based on new crops such as Camelina carinata, but many of these crops are not actually currently growing. So there's an estimate of potential which doesn't really give actual availability. There's also, for example, mention of jatropha, which I think has been shown to not really be effective and has not really taken off at all. So the other thing, of course, is that availability without established supply chains don't really mean much. So there can be estimates of availability, but unless there's a mature supply chain being put in place at the same time, that feedstock may not really be available. And then from a technical perspective also, pointing out that feedstock density will limit transport distances and the size of the facility. And for most technologies, the feedstock must be sourced within a limited radius. And the figure that I've shown there at the bottom, so it shows the biggest HEFA facility, renewable diesel facility, which comes at 1.8 billion liters per year. That's Singapore. And the blue section is leveled off at about 1 billion liters per year. And by comparison, at the bottom, recently announced facilities that will be built or are currently being built of about 40 million liters per year for the total facility. And you can see the comparison with HEFA. And even if there's an increase of 3 times for larger facilities down the line, they are still going to pale in comparison with the HEFA facilities. And that's really just based on feedstock density, because lipid feedstocks can be transported over long distances, but other feedstocks such as residues and so on cannot be transported unless there's some kind of densification in between. Next. So if we look briefly at technology platforms and ASTM certifications, ASTM D7566 has 7 currently approved technology pathways, and ASTM D1655 has 2 types of co-processing that is approved. And there are many other pathways in progress towards ASTM certification, and this is exciting and is certainly some measure of technology commercialization, but many of these pathways are not commercial yet. So currently maximum blends are limited to 50%, and there are many reasons why this should really be increased. I'm going to talk more about that. And although fast track certification is possible, it is limited to 10% blending, and this will be a significant constraint for those technologies to, deliver significant volumes. And then currently the maximum blend for co-processing is 5%, and this is definitely too low and will limit any contribution from this pathway. Next. So you might have seen in the news many studies. Rolls-Royce Airbus announced flying on a SAF blend of up to 100%. And when I first saw that, the question was, is this even relevant? I mean, we don't even have enough SAF for a 0.1% penetration. And secondly, is this feasible when SAF has no aromatics, current SAF like HEFA, and therefore this cannot be considered a drop-in fuel. So there are really 2 reasons why 100% SAF is considered. Firstly, the whole issue of the book and claim system, which I'll discuss in another slide, and then the non-CO2 climate impacts of aviation. So with the introduction of a book and claim system instead of a mass balance system, SAF can be used at one place and claimed at another, and I will discuss this. But what can happen is that airlines might want to use 100% SAF at large airports to achieve significant overall SAF consumption, because other airports may not use any SAF. And then secondly, the important issue of non-CO2 climate impacts. So 100% paraffinic SAF has been shown to significantly reduce non-CO2 climate impacts of aviation due to reduced soot formation, which then reduces persistent contrail formation. And this is based on a recently published study from NASA and the German Aviation Research. But this was obviously based on HEFA SAF, which is 100% paraffinic, and is therefore not a drop-in fuel and not compatible with all existing aircraft and fuel infrastructure. So to reduce the non-CO2 climate impacts while maintaining a drop-in fuel, what can happen is that the ASTM specification can reduce the maximum aromatics currently at 25% volume, but it can be as low as 8%. So by reducing that maximum, some of the non-CO2 climate impacts can be achieved without changing the entire infrastructure system. Next slide. So I talked about the book and claim system, and although these are seen as two separate things, also the issue of SAF certificates, because for me there is an overlap. So book and claim system is very important to the sector, the airlines, because it means that SAF does not have to be transported to every airport, and that it can be used at the closest airport to the production facility. Of course, this will reduce transport, and it will also improve the potential carbon intensity of the fuels. So what this means essentially is that if you look at the diagram, is that the SAF is separated into two components. On the one hand, the physical fuel, and on the other hand, the sustainability characteristics of the fuel. And so the physical fuel can still go into an airport and an airline, but if the sustainability characteristics have been separated, then essentially that physical fuel will be similar to a fossil jet fuel. So an airline who buys the fuel and then puts it into their airplanes can claim the sustainability characteristics, but the other potential is that the sustainability characteristics are recorded in a SAF registry and can then be sold to customers other than airlines, such as corporate customers. And this is where the SAF certificates come in, and there will have to be some kind of overlap. And you might have seen, I think last week, the WF Clean Skies for Tomorrow published a interesting report on establishing a SAF certificate system, because there are lots of corporates who have business travel, which contribute to their emissions, and who want to actually reduce emissions in sector rather than buying offsets. So this will allow them to buy the sustainability characteristics in the form of SAF certificates. But that physical fuel then used within an airline will not actually have that sustainability characteristics. So that is important, because if there has to be strict chain of custody, and traceability will be essential then to avoid double counting in the system. Next. So now I'm going to switch to the technologies and really look at a couple of the technologies, not all of them, and the trends that's been happening, and the potential and challenges for these technologies. So as I said, HEFA is currently the only fully commercial pathway and be the main supplier over the next 10 years. And this is also because of the possible volumes that HEFA can more easily produce due to the larger scale of the facilities. So commercial scale facilities for gasification, Fischer-Tropsch and alcohol to jet are being built and will proceed towards full commercialization, obviously if everything goes according to plan. And then other technologies will take longer. But I think what's also interesting is that companies are not limiting themselves to one technology, but are exploring multiple technologies with potential integration. Next. So just to talk about the HEFA, so what we are seeing is a significant increase in production capacity, mostly for renewable diesel. And there is increased SAF production by separation of the jet fraction in existing facilities, and also increasing the jet fraction through additional processing. obviously, there's also to keep costs low and improve sustainability. There's an increased sourcing and use of waste fats and oils. But because of the issues with potential contaminants, say from brown grease, there is a need for increased pre-treatment. And whether the pre-treatment takes place at the renewable diesel facility or with the supplier of the feedstock will become an issue as well. And I think World Energy is potentially going to start pre-treating their own feedstock to ensure the right quality. And what we are also seeing is that HVO producers are investing in or acquiring feedstock producers to secure a future feedstock supply chain. Next. So what are the challenges of HEFA? There aren't really any technical challenges, but the challenge really lies in feedstock cost, availability, sustainability, and quality. And as you can see here on 9 November, the published price for used cooking oil in USD was $730 per ton. And that is already higher than the cost of a ton of jet fuel. So we've talked about feedstocks, and specifically waste feedstocks for HEFA production. There are various estimates. I've seen 25 million tons of waste feedstocks, up to even 100 million tons, which includes cover crops and crops on marginal lands. So it's and up to say even 40 billion liters per year of renewable diesel, with obviously a fraction of that being SAF, say 20 billion liters. But there isn't really enough data on these waste feedstocks. So crop-based feedstocks in many cases are completely avoided due to perception and potential sustainability issues, which is possibly controversial. And in some cases, in some jurisdictions, crop-based feedstocks may be allowed, which can significantly increase potential volumes of SAF production. But there's also competition with biodiesel for feedstocks, and even the catalytic hydrothermolysis process uses lipid feedstocks. So there will be competition. And although there are many newly developed feedstocks, such as camelina, carinata, saliconia, these are still immature feedstock supply chains and currently at low availability. Hopefully this will increase. And then, as I highlighted, the competition between HEFA for aviation and HVO for road transportation, and that policies such as the multiplier is essential to put them on an equal footing. Next. So opportunities from the HEFA is, as I pointed out, the high feedstock density allow large-scale facility and in economies of scale, which the other technologies cannot really achieve. And easily, HEFA facilities can produce 15% SAF if the incentive is there, and then further expansion to maximum SAF. So if maximum SAF is implemented, there can be billions of liters available quite quickly. And what we are also seeing is that HEFA producers are improving sustainability characteristics of their fuel through production of green hydrogen, say from the propane byproduct, in order to improve even beyond the 80% reduction in emissions. And the competition can be addressed through policies. Next. So if we look at gasification and Fischer-Tropsch, obviously you would have seen that Fulcrum Bioenergy just completed their Sierra Nevada facility, and the Red Rock Biofuels is under construction. But these are still pioneer facilities, and once they are actually in operation and successful, I think there will be a significant acceleration of more facilities being built. And so far, two feedstocks. Main feedstocks are targeted municipal solid waste and residues, and this can achieve significant emission reductions. Next. So challenges of the gasification and Fischer-Tropsch. There's been a very slow commercialization since first ASTM certification in 2009. And some of the biggest challenges was tar formation and feedstock contaminants in the syngas. And this is particularly because of biomass-based feedstocks. And there are many ways to address this through gasification technology, which delivers a cleaner syngas, but that will be at a high cost. So there have been, there's a balancing act in terms of putting each of the components together. And the syngas cleanup, although technically possible, it's really balancing the quality and the cost, because although the gasification is the biggest cost, syngas cleanup can quickly also add up and become a really significant cost that could be prohibitive. And because biomass has high oxygen content and so on, you will get a low hydrogen to carbon monoxide ratio from the bio-based feedstocks, and that needs to be corrected through conditioning of the syngas. This technology also has a very high capital cost, and unlike Fischer-Tropsch facilities based on natural gas or coal, economies of scale is difficult based on low feedstock density of say, woody residues. Next. But the opportunities for gasification Fischer-Tropsch is really that they can use waste feedstocks that are available in very large quantities. And it's also one of the pathways that can produce very, very low carbon intensity reductions. Fischer-Tropsch liquids can also be used in co-processing, because after you've produced the Fischer-Tropsch liquid, there still needs to be further hydrotreatment and distillation in order to separate the fractions. So you can skip some of that infrastructure by co-processing. And current research, although you can produce currently about a 40 to 50% jet fraction through normal Fischer-Tropsch, current research is really focusing on how to increase that jet fraction by up to 80% through catalyst improvement, bifunctional catalysts. And obviously with SAF being the biggest target, I think that's very promising. Next. Now, if we look at direct thermochemical liquefaction, and this includes hydrothermal liquefaction, fast pyrolysis, and catalytic pyrolysis. So there is no SAF being produced this route, but because of the potential of this technology, I'm going to go into some detail. So this technology is still at various stages of technology readiness, and there's still ongoing work into upgrading of these bio-oils or bio-crudes into finished fuels. And this will also be suitable as a bio-based intermediate for co-processing in refineries. And as I mentioned, the whole issue of feedstock density, pyrolysis or HTL can produce a liquid product at a higher energy density and can potentially then be used in a distributed supply chain to support larger facilities with improved economies of scale. And HTL for SAF production is very promising. A few weeks ago, the HyFlex Fuel project announced that they've looked at SAF fraction and with very promising results. And because they can use, HTL can use niche feedstocks such as sewage sludge and other wet waste, I think it's promising in terms of expanding the access to different waste feedstocks. And then the other thing I wanted to also mention, I think, is the co-processing. Although co-processing of biocrudes is currently at a very, very early stage, hopefully by 2030, this could become a more significant contribution in existing refineries. Next slide. So challenges of this technology, the direct thermochemical liquefaction, is the complexity of the bio-oils, biocrudes, and the variation in the bio-oil characteristics with the type of feedstock. And then upgrading. There have been technical challenges, catalyst inhibition, and catalyst lifespan and cost. And these are all still being addressed. There's also a higher hydrogen requirement for upgrading, and that depends on the oxygen content. For example, fast pyrolysis bio-oil has about 45% oxygen, and even though some hydrothermal liquefactions, biocrudes can go down to 8%, this is still a significant amount of hydrogen that has to be used, and hydrogen obviously will also need to be used for cracking aromatic rings and so on. And then certain feedstocks such as algae also has a high nitrogen content, which is also removed through hydrotreatment and increased hydrogen. So currently there's no ASTM application in the pipeline for any of these technologies. And one of the issues has been limited volume availability for testing. And SAF production is possible, but still needs extensive development. And one of the projects that Jack mentioned, the ATM project that we were engaged in with Boeing, actually looked at SAF production and with very promising results, but for a significant SAF fraction that can meet specifications. So hopefully ASTM certification applications will happen in the near future. Next. So opportunities for this technology, as I said, the fact that biocrude production can be a form of densification to support the distributed supply chain, and this is happening in some cases. So even supporting gasification, so entrained gas flow gasifiers require really small particles, and making a biocrude first could potentially solve this kind of problem. There's significant potential for co-processing, and then it can utilize cheap and sustainable feedstocks that is available in large volumes, with HTL specifically very flexible in terms of using wet feedstocks as well as other feedstocks. Next. So alcohol to jet, I think there's been a lot of news about alcohol to jet, and it's quite exciting. Two of the main producers I'm going to discuss is the Gevo, which produces isobutanol, which is then upgraded to jet, and the LanzaTech technology, and specifically then LanzaJet, which can upgrade the ethanol into a jet fraction. And there's multiple ways to get to the actual alcohol. And so the jet production step from alcohol to jet is fully commercial, but currently the isobutanol is only delivering small demo quantities of fuels. But the first full-scale commercial facilities are actually under construction. And one of the significant advantages of this technology is that it can produce up to 70% of a jet fraction, with the remainder being naphtha. Next. So challenges of the alcohol to jet, because the first step is really a biochemical step where there's a fermentation, the yields of alcohol can be low. So compared to Saccharomyces cerevisiae, which is used for normal ethanol production, very high yields can be achieved, but for other organisms, yields are still lagging behind. In the case of butanol, whether N-butanol or isobutanol, this is toxic to the fermentation organism, which will also limit its volume production, and the cost of separation of alcohol from the fermentation broth. Now, what we have seen, for example, with Gevo is that they've got a specialized system that is continuously removing butanol from the fermentation broth, and they are able to increase their yields quite significantly. Then also these alcohol intermediates can be used in other applications such as the chemical industry, for plastics, bioplastics, and so on. So they have a high value in itself before having to put them through further processing. So there is definitely a competition with other applications. Now, many reports and so on talk about potential volumes of alcohol to jet SAF, but based on cellulosic feedstocks. Now, this is actually freestanding facilities for cellulosic ethanol production has had limited success and difficulty in commercialization in spite of very, very strong policies. So projections for alcohol to jet production from biomass is probably quite unrealistic. And use of crop-based feedstocks such as corn is easier and cheaper, although more controversial. But for example, GEVO has shown that with other putting in place other things like renewable energy, they are able to achieve a very low carbon and even a net zero fuel based on a corn feedstock. Next slide. So opportunities for the alcohol to jet, because you can actually use an current ethanol facility and convert it, repurpose it. This can make the infrastructure cost much cheaper. There's a lot of options for genetic modification of strains for higher yields, the potential for low cost waste gases for ethanol production. In the LanzaTech case, you can achieve a high fraction of jet, and the alcohol to jet technology is established, but continued improvements, specifically reducing the number of steps for ethanol to jet, is a research target. There is ASTM certification for isobutanol and ethanol, and further alcohols should be reasonably easy. And then combined with carbon capture and storage, very low carbon intensity can be possible. Next. Lastly, really want to discuss the power to liquids. And this is obviously based on carbon dioxide that can be sourced from the air or from a point source, and electrolysis of water. But although this technology has great potential because of low land requirements and potential for net zero, it is not really, as an integrated step towards SAF production, is not really far advanced in terms of technology readiness, and some of the steps still need to be commercialized. But there's a lot of excitement in the EU for this, with a potential dedicated mandate that could be announced. And Germany specifically has announced $10 billion funding for hydrogen technology for SAF production from power to liquids. Next. But the power to liquids is currently one of the most expensive pathways, and there has to be sufficient renewable energy for hydrogen climate benefits. So your grid should ideally be 100% renewable. And the competition for renewable energy will also come from heating and electricity and electric vehicles. And it's important to note that power to liquids is an inefficient way to use electricity, as use of electricity for electric vehicles are 6 times more efficient than e-fuel production. There's also very high costs associated with direct air carbon capture, and a potential problem with point source capture and sustainability, and the issue of double counting. And the integrated pathway is still at an early stage of development. Next. But the opportunities for this technology is really very significant emission reduction and theoretically unlimited potential, as it does not use biomass feedstocks or need arable land. And only really sufficient renewable electricity could be limiting. It could also use electricity grids as partners with e-fuel acting as an energy storage, and there's a high potential for long-term cost improvements based on cheaper renewable electricity. Next. So other technologies that I've left out really is the farnesene and catalytic hydrothermolysis with various issues, but I think that the farnesene has a far greater value as a product in cosmetics and is unlikely to really produce or contribute significantly to SAF. And then my last slide, sorry, Jeff, I've gone a bit over your time. Next slide. So the conclusions really is that the HEFA is fully commercial and will continue to be the main technology supplying SAF for the next 10 years. But this can be increased even with conversion of existing renewable diesel facilities to produce a SAF fraction. Commercialization of all technologies should be pursued. And while technical challenges remain, the high price difference is really the obstacle, and policies are essential, but should be linked to carbon intensity. And I think that overall, the message is that SAF development is really gaining incredible momentum, and there's a high level of optimism, and it will be, the next few years will be exciting to see it taking off. Thanks. The next slide, Lapo. Yeah, my email address is available there if you want to send me any questions.
Thanks, Susan. This is a great in-depth report on the tech available for SAF. So today, I know we're deep into this presentation. So I'm Jeff. I come from a former airline background where I was asked to put in place our low carbon and SAF strategy, but I also had the opportunity to manage our fuel procurement department as well. So I blended both departments. So an interesting a way of looking at SAF coming from the procurement side right off the bat. And of course, my training as an environmental engineer, being able to kind of sort of look at those efforts. An interesting observation I've always made is in normal conventional jet fuel, it is on the lower end of the price scale, you know, usually tracking a little bit under diesel, just happens to be made with some of the processes. And ironically, in the clean or the green piece of making SAF, it's on the more of the higher cost products because there's extra effort involved in making it, as you saw in Susan's presentation. So I always thought that's an interesting sort of fact. Next slide, Lapo, please. I just, you know, today I'm just going over what aviation has done and is doing in terms of its climate plans. Under ICAO, aviation was one of the first global industries to come together to develop a climate action plan. And in that plan, you know, they targeted obviously fuel emissions and then improvements in those year after year. Recently, as of 2020, the carbon neutral goal was instituted, and along with that comes this program that was implemented called CORSIA, which is a program where growth emissions are priced, and airlines have obligations either to buy market-based measures or use SAF to reduce that obligation. In fact, this is the first period of CORSIA that's in place today. The ultimate aspirational goal that aviation had set itself, you know, years back is a 50% reduction in GHGs by 2050. There are various levers, and they've been bucketed into 4 various pillars that aviation can use: technology improvements, i.e., you know, new aircraft, new engines, which typically yield, you know, a significant 10 to 50% reduction opportunities in fuel use. Operations, of course, fuel is a precious resource. It always has been. Aviation spends a lot of time ensuring that we can use it as efficiently as possible. And that includes looking at how we fly the aircraft, you know, how airport or air transportation control are made, and how we can optimize the routing through those systems. Infrastructure is an important piece. The airports, how they're designed, what kind of sustainability initiatives can be implemented in terms of design and reduction of taxiing time, so on and so forth. And then, of course, SAF is a big piece of this, and we'll go through in a minute here why it's so important for aviation. And along with this, of course, there's been pressure to develop more significant targets, and that's why you're seeing a lot of airlines come out with net zero emissions as well. Next slide, Lapo, please. The industry, through its associations, have spent some time recently developing and getting some scientific target setting around the 2050 target, and various backcasting exercises looking at the scenarios that could be tweaked, either going aggressive on technology or implementing SAF more aggressively as well. The various scenarios looking at how the 2050 target of 50% reductions could be achieved. And the important thing of this slide, and thanks to my friends at ATAG, obviously, for presenting or preparing this, is that SAF still will do the heavy lifting in terms of helping aviation achieve its emissions. So whatever scenario you look at, SAF is still a major player in that scenario. Next slide, Lapo, please. When we look out to 2050, even with the introduction of electric aircraft, which I think the focus for electric aircraft will be on shorter length or shorter duration flights, and hydrogen being introduced as potentially a different energy source, the energy density of the jet fuel is still an important factor for escaping the physics of Earth. So there's still a large percentage of SAF that is going to be required by aviation to be able to decarbonize. Next slide, Lapo. I was going to take the opportunity just to give you my perspective as a former airline person asked to put in place our SAF and low carbon strategy. And sort of the journey that we took from the beginning, where as everyone else several years back, learning about what SAF is and how to implement it. We went through various stages of how, and as Susan indicated, price is still a huge issue, and how we would overcome that price. And there are various methods of getting there. Do you simply wait for the market to respond and buy the fuel when it's available? Do you become an innovator and try to innovate your own clean tech within the airline, which of course you're competing against other dollars for investing in fuel efficient aircraft? So that's not the easiest process, although you have seen some airlines obviously make some equity investments in the States, for example. There's a few opportunities that have come forward with that. Or as we looked at it, policy and the regime that helps everyone invest in the long term for these biofuels is really the key impact of what we felt we could influence to be able to get long-term SAF production in the area that we operate in. And that's what we decided to concentrate on. Lapo, please, next slide. This is just a bit of the flow diagram that I continuously would go through when we were looking at opportunities. You would start with the region that you were working in. What kind of techs are available. Those are usually the first people to come to you with opportunities. But that quickly, forces you to look at, well, what are these techs going to use to convert into to make the SAF? Then you end up trying to figure out whether or not there's enough reliable or robust feedstock that in a sustainable way as well, because the airlines are forced to meet various compliance, whether it be international or domestic. And then you find out that that's a very tough job and very expensive. And then you come to price and feedstock. If you look at the various reports, I think Susan goes into it, or IEA goes into the report as well. Feedstock is a major input to that cost. And so there are various ways of impacting that. The biggest one is just the policy. Everywhere you look at it, there's going to be some form of incentive to be able to make SAF work. When I look out, SAF is, I like to describe it as like a tiny island in this huge ocean of ground transportation policies. And therefore we're battling just the unique business that we operate under, but we're also battling, the huge volume that might be created for the ground transport system, which of course has a lot different options than aviation. So when we say aviation is one of the hardest to decarbonize, that is true. We can use SAF. Yes, there are electricity and hydrogen coming through, but as I said before, SAF is that main key ingredient that we need. So how do we work with government in order to sort of get a piece of the pie to ensure that we will have the SAF where it starts developing, so that we can have it later on when we really need it, when other modes potentially have decarbonized. Next slide, Lapo, please. So yeah, ICAO does a great job at tracking some of the initiatives that are ongoing. You can see here they contain a graph of areas where you can buy SAF. And again, you're seeing it in areas where there is friendly policy. I mean, I put a question up here, you know, as various countries implement new low carbon fuel standards and such, you know, what is that going to mean? You know, producers are incented to produce renewable diesel more than SAF. And I think Susan went through some of the reasons for that. And what is that going to mean? What does the pressure on feedstock mean? So there'll be some interesting sort of impacts, I think, going forward on that. In the top corner, you know, CAFE does a great job at tracking the production estimates for going forward. You can find all these slides on the ICAO and the CAFE slide, but you can see there is a growing production of SAF occurring with incentives generally is where you're seeing the production occur. And so, you know, that just justifies the need again for coming up with sound policy to support the SAF production. Next slide, Lapo. So what have we learned after all this? You know, we need to work together to create that SAF market. Aviation is a small piece of the bigger piece of the pie. You know, we need to be very vocal in terms of trying to create that market so we're not forgotten at the end of the day. It is a must. We need SAF to achieve our 50% reduction. We're going to need even further to get to net zero, combined with other creative policies or other opportunities such as, you know, carbon storage or the PTL fuels, for example. We need sound policies to support aviation and SAF. We need to be able to compete against ground transportation policies, at the very least making it equal, so that suppliers have an opportunity to use the SAF as there's a compliance pathway that they need to meet. It's very important that those two be considered, as well as the extra effort and cost to produce the SAF, and how we can sort of make up the gap around that. What we have found is that, you know, it's successful deployment when government and the aviation sector works together. And I think there are, you know, through various organizations or organizations that we created, we're in Canada just about to launch the Canadian Council for SAF that will help us lead the way in terms of what we need to do in terms of deploying stuff. It's at initial stages of launch, but that's an example of bringing the whole SAF ecosystem together to be able to create the right smashing of innovation to be able to create these SAF value chains, and that represents that common voice, that push and the industry pull that I think Susan went into, that will be able to create with government and with some of the other partners the right regime over the long term to support these SAF initiatives going forward. I have to give a kudos to the IEA report. You know, as an airline, you know, it's technical, but I think it's important that you understand what the challenges are with these various techs and how they relate to the feedstocks. And I think that report does a really great job of just giving you the state of technology today and where it stands, and you know, it gives you a good appreciation of what you have to think about if you're either entering in, even if you're entering into a fuel purchase deal, you know, the challenges that some of these techs are presenting along with the feedstock, and you need to understand that to be able to ensure that you negotiate a great either long-term uptake agreement or pricing going forward. So thank you.
Thank you very much, Jeff. And thanks to all the panelists and everybody for your good questions. We've got a few questions have been answered, but we've got a couple dozen more that have been posed, and I want to encourage the audience. I see some people are starting to upvote questions, so use that tool to upvote them so we can get the ones of greatest interest answered. And just to kick that off, one that has gotten a lot of upvoting is a comparison to the development of biofuels for transportation fuels as compared to hydrogen fuel cell vehicles. And I think we also saw this in the aviation. Why is hydrogen considered as a future when it would be easy to replace biofuels as compared to that of hydrogen? And I guess easier to use biofuels than hydrogen. Hydrogen requires a lot of infrastructure to be developed and a lot of money is involved as compared to that of biofuels. So wondering if there's any comments from the panelists, particularly, well, any of the panelists on the issue of hydrogen. I think it's quite important in the production of SAF as well, biojet.
So Jim, I'll just kick off and maybe Susan and Jeff can add their comment. I mean, my own sense is, just as you said, the infrastructure requirements, it's producing the hydrogen, storing the hydrogen, moving the hydrogen around. I think it will be pioneered on land transport. So we'll be using hydrogen initially in things like buses and those areas. And once we've pioneered a lot of the hydrogen in that infrastructure, I think then we can possibly think about it in aviation. But probably easier to try and pioneer the various challenges with hydrogen in kind of land transport before looking at aviation or marine. But Susan and Jeff can add their comment.
Yeah, I agree. I think hydrogen is going to be an important piece of the ground transport, but even from developing SAF and some of the opportunities, we're going to need some hydrogen to do that as well. And when you look at even the refining community, there are opportunities for developing lower carbon fuels exist around the hydrogen that they use as well. So I think there's probably some more efficient uses of hydrogen to start with, and that obviously will develop the supply, and from there maybe we will see kind of the extra infrastructure required to move to other modes.
Susan, any comments? Okay.
I would just mention also that a number of the IEA Bioenergy Task 39 countries and members of other countries as well have active programs in both biofuels and hydrogen. So it's not really an either or, it's an also and to really bring renewable lower carbon technologies forward. One of the comments that has been upvoted a lot is thanking you for a great presentation, Susan. So it's more of a comment than a question, but I just wanted to get that out there. A lot of people have said that. Another one is about different countries opting for different pathways, feedstocks, and how certification will take place. And maybe the import of certification could be discussed briefly. Would anybody want to take that on? How important it is? I mean, we say SAF, but how do you verify the sustainability attributes and the importance of the feedstock and so forth? Anybody want to comment?
Yeah, I'll go for that one. Obviously, there's certification in terms of the safety aspects with ASTM, and I use ASTM because it's sort of a standard, but they are in the UK they use the DEF stand, and in Europe and even in China there might be others. So that's from a safety perspective. But then the certification from a sustainability perspective, I think really what has happened is that fuel producers and airlines have used, for example, RSB to certify their fuels. And now CORSIA is establishing a framework for sustainability, which is being followed. So I think that is probably going to become the standard. But what you see is that CORSIA has a limited set of sustainability criteria. And what RSB and ISCC is doing is they can certify a fuel according to CORSIA, and then they have a stricter standard, which they then call ISCC plus or RSP plus, where, for example, in the case of RSB, a 60% emission reduction compared to with CORSIA that requires a 10% reduction. So that's really via the sustainability certification schemes such as RSB and ISCC that the certification will have to take place.
Thank you. There's please.
So Jim, I'll just add to Susan. I mean, Susan covered it in her presentation. I think, feedstocks such as used cooking oil, they should have a low carbon intensity. It's a true waste. So I think As Susan covered in, there's going to be probably a used cooking oil feedstock is going to be more valuable than, say, a vegetable feedstock that's had much more carbon inputs in terms of fossil fuel. So I think it's going to be interesting that the certification on the carbon intensity is going to have an impact on the value of the feedstocks, because there's only so much used cooking oil out there. So I think it's going to be interesting to see how the certification, the policies do impact the value of the feedstocks.
Yeah, and we need strong certification programs that people can believe in, because there's been a lot of gaming of like used cooking oil, you know, dropping a little in and calling it used because you can get a better value for it. There's a question about the Refuel EU that's sort of related. Does it require a minimum GHG savings to qualify under that volumetric mandate? And I know you mentioned that, Susan. That mandate is going to be announced tomorrow or something. But
well,
you know?
the full proposal will be announced tomorrow, and then I think there's still negotiation on it. So we'll only know really what's in it after tomorrow. Hopefully, there is a link to carbon intensity, because I think it's really important to push technology producers or providers to really try to achieve the net zero through additional infrastructure and inputs.
Agreed. The US RFS is a minimum 50%, and I would assume that the EU would do at least 50, 60, 70, something like that. But we will see. Are there, so this is a little different, but there's a question about efforts worldwide to convert biogas from anaerobic digestion into renewable hydrocarbons such as SAF. Do any of the panelists or any of you aware of those kind of activities?
Well, obviously there are very large scale facilities using natural gas through a Fischer-Tropsch to produce hydrocarbons, and essentially biogas can be used as a replacement. I think the problem is going to be the volume available, and of course the fact that natural gas, well, biogas will also be able to be used for other applications. So yeah.
Yeah, so Jim, just to piggyback on what Susan's saying, I mean, I think it will be demonstrated using, say, natural gas. So can you actually make it happen technically? And then the market, if you're able to get a green source, like renewable natural gas, the market then will start driving use of things like renewable natural gas rather than natural gas. So I think technically it will be demonstrated using natural gas, and then the market will piggyback on a lower carbon intensive fuel.
But I also think that, you know, an integration of different types of technologies is going to happen. For example, Gevo has anaerobic digestion that produces biogas that they then use for some of their heating and electricity requirements. So that kind of integration will deliver lower carbon intensity fuels.
Okay, thank you. There's a couple of questions related to price. The first is, what would be the carbon price to make SAF competitive with conventional jet? And I think that's very challenging. What's the feedstock you're starting with in you know, the situation? But so one is the carbon price to make SAF competitive, cost competitive, and the other is about a price forecast. Is there a price forecast for SAF in the 2030 to 2050 timeframe for both SAF and renewable diesel?
Well, in terms of the price forecast, I would suggest looking at reports such as the World Economic Forum Clean Skies for Tomorrow report, or even the Waypoint 50 reports. But of course, it's all just projections of how the price will be reduced. In terms of the carbon price, no, I don't know. I haven't actually done any of that analysis. But what I do want to point out is that you place a value on the carbon, but there's a difference between having merely a carbon price and the way that SAF is integrated in policies such as the low carbon fuel standard in California, because you know, the low carbon fuel standard, there's a direct benefit to the fuel producer, whereas the carbon tax is going to disincentivize the emissions, but is not going to directly help the producer.
So Jim, I mean, I'll ask Jeff to ask his bit, but my sense is Susan's covered eloquently for the HEFA route, which is going to dominate. It's a feedstock cost. It's not really technology. So the way of reducing the cost with HEFA is the feedstock. That's where to emphasize how to reduce the cost. And then the hope is that with the other technologies is that will reduce, because hopefully, say a MSW or a biomass feedstock should be cheaper than a lipid feedstock. So as these technologies mature, so I think this is why very hard to predict what the cost will be, but there are opportunities in the HEFA pathway to reduce the cost of the feedstock. And with the other processes, technology, I think, will reduce the cost. But Jeff, what do you think? You're going to be buying this fuel.
Yes, that's right. I mean, I've always equated, like, if it's even twice as much, I think it's something like $400 or $500 a ton. I think if you use the current kind of jet carbon conversion numbers. So, you know, I think the world is still far away from that number. But you're right. I mean, aviation price, I mean, look, fuel is probably usually in the top three components of an airline's price. So, you know, what is the ability to transfer that to people flying? I guess that's the second piece. And so it's hard to plan 10 years out. The cost is what it's going to be. We don't know what crude is going to be 10 years out. I mean, there's forecasts for that as well, and that drives the price of jet. But still, I think, you know, we need to find, you know, and then of course we have increasing carbon policies that are coming in place that we know of, and you know, you would assume eventually that carbon price you know, converges to a price around the world that would make it easier for everyone. But I agree. I think that's where the creative policy piece needs to come in, because the feedstock and it is really, you know, the biggest driving force behind the cost. I mean, like Canada looks at canola and they export whatever 85% of it. So is that a potential source? I mean, you're talking about food security, but you're also, it's a huge import or export, sorry, for Canada. Can we use that? But a barrel of canola is, you know, 2-3 times more than a barrel of jet to start with, right? So it doesn't make for a great start if your input costs are way higher than what you're trying to replace. But, you know, we need to move around with what the world needs us to do, and we're gonna have to take some creative looks at how to address those situations.
Thank you. There's a couple more questions here on that a little difficult to interpret, but I think the one speaker, Alexandre Schlecko, is asking that wouldn't the ideal be to use vegetable oil for HEFA and HVO, given the difficulty of decarbonizing the hard to abate sectors, shipping and aviation. I'm not quite following that, but couldn't this be a policy proposal considering the synergies between IMO and IATA's targets? So I don't know if one if people can interpret that better than I can. The other question there is, would it be better to focus the reaction that converts pyrolysis oils into distillates on decarboxylation rather than hydrogenation in order to avoid the huge hydrogen demand? And I guess, you know, there's obviously a yield trade-off. It's all about economics, what makes sense. Did anyone of the panelists follow this policy proposal, the synergies between IMO and IATA?
And I think, Jack, you can correct me, right? I think there's a natural, the product that's produced with SAF, you know, the other product is a natural complement to some of the shipping requirements. So maybe there is an opportunity there to look at that. I think it's back to, you know, how can we ensure we get a piece of the low carbon fuel pie, considering that most of the sort of the policies are directed towards ground and transportation. But yeah, anything to combine together the volume to make it work, I think is a great idea.
So
Yeah,
sort of the, yeah, please.
Yeah, sorry, Jim. I mean, as you know, I mean, the work we've been doing in Task 39, as Susan knows, on co-processing. I mean, as Jeff's referring to, if you go in and you do co-processing with a lower carbon intensive feedstock, you're going to lower the carbon intensity of the jet fraction, and you're going to lower the carbon intensity of the marine fraction. So I think the ability to go in and do processes like co-processing, you're making use of the current infrastructure, the allocation of where the lower carbon intensive molecules go, it all depends. But I think it's one way to get some good synergies between the marine sector and the aviation sector, because they use different fuels. I mean, one's tends to be a high spec fuel, the other one's a lower spec fuel. So I think co-processing is one way to get the synergies for both those sectors.
And that's where policy could play a key role in helping that to come along. I don't know how much more time we have. We're close to the end of our scheduled time. There's one comment here on the alcohol to jet, which I think is an area that's getting a lot of attention. And there was mention of high interest in ethanol for the chemical industry, but then this person is saying, but the chemical industry will not pay for 2G ethanol, and I guess, or lower carbon ethanol. And I guess I would respectfully disagree. For some products, they may want to show a low carbon intensity, and they would indeed pay. But do panelists want to talk about that, the premium for green molecules? Willingness.
Yeah.
Well, I
so
think
Jim,
the US Renewable Fuel Standard incentives, the RIN incentives, obviously make it very beneficial for the 2G ethanol to go into transportation. So in that sense, yes, it is correct.
Yeah, no, Jim, I agree with you. I mean, I think the market's going to end up looking at where those molecules, but I think we're kind of being told to wrap up here. So if I look at the chat box, it's we've run out of time.
Yeah, I think there's additional questions that have been posed, and we will share those with the panelists, and they will have an opportunity to respond to those soon. I think that's, and I don't know if Marco or anybody else on the IEA Bioenergy webinar side wants to comment on that, but the presentation and the recording will be posted on the IEA Bioenergy website tomorrow or very soon. And we will send out answers to remaining questions by email to participants. And with that, I'd like to thank you all for attending this webinar. I want to thank our speakers again for their excellent presentations and all the attendees for their excellent questions. And I think with that, I conclude today's webinar and wish everyone a good day.
Thanks a lot, Jim.
Thank you, Jim.
Bye.
Thank you, Jim.